we started chapter, is it chapter 7? It's chapter 7, right? On rotational motion. And all this was the same, it's just we had a few things that were different. A couple things to note is that we're using radians. You'll need to know how to convert between radians, degrees, and revolutions. So I gave you this conversion factor, which is at 2 pi radians equals 1 revolution equals 360 degrees. And then we also had basically our kinematics equations and all of our definitions, where we're letting x now become theta, v becomes omega, and a becomes alpha, so that we get these equations for our kinematics. And we'll work through a couple of problems. We've already worked through a couple, but I'll work through another. We'll look at some of the homework. So, for example, our equations now are theta equals omega naught t plus 1/2 alpha t squared, and then also omega equals omega naught plus alpha t. And then also our same definitions are still hold true. That is that omega is the first derivative of the position function, and alpha is the first derivative of omega. The angular acceleration is the derivative of velocity, and the angular velocity is the derivative of position. That was just like we had in chapter 2, but you'll see it again. And I think we worked through a problem last time where we just had to take the derivative of a function, correct? Pretty sure we worked through one like that, and had to find various things about the motion. And then also we had, sort of at the end, we had these relationships. This can take an angular velocity and convert it into a linear velocity, or an angular position into a linear position, or an angular acceleration into a tangential acceleration. So for example, if I have an angular position here, theta, I move through a certain angle theta, then this distance, say I have a particle that's moving along this semicircular path, is equal to theta times r. Y'all probably seen that before in high school geometry. Arc S is equal to theta r. And in a similar way, we can relate our velocity and our acceleration just by multiplying the angular quantities by the radius. All right. You should be able to see this because the units here, radians per second for omega, and meters. And so when I do these units, they just become meters per second. That radians just sort of goes away. It's not a real unit anyway. And then similarly here, I have radians per second squared, meters, and that's meters per second squared. All right. Let's see, we worked through this problem. Let's work through a homework problem. Is that okay? Have y'all done all the homework yet? All right, of course, right. Let's take a bit, and we'll just work through a homework problem in class. And then we'll come back and we'll talk about centripetal acceleration. No, I'm just going to make up one for you. You have the solutions to all these. So you can write wherever you have, like there's a blank page on page 223. So try to just take up a half page because we're going to use the other half of that. So let's say that I have an object. Sorry, let me think for just a second. An object starts at rest and rotates through 3 revolutions in 2 seconds. What is its final angular velocity? Final angular velocity.
take a moment. There are a couple things you'll need to do right off, like, well, no, you don't have to do that. Never mind. Just write down everything that you know, and then write down what you want to know. You can write down your equations. If you forget them, I'll write them right over here. What are some things that I know? Yeah, I'll just keep working.
So,
Hmm?
so, and
All right, what are some of the things that I know here? I have some quantities that are given. What are they? What's that, Joseph? All right, okay, I know time. Time is equal to 2 seconds. What else do I know? I know the total distance, or the angular displacement, so that's theta, and it's equal to 3 revolutions. You can convert that to radians if you wish, but I didn't stipulate it in the problem. So if you ever have questions, you can just go ahead and convert it to radians. You'll never go wrong converting it to radians, unless I ask specifically for the units and revolutions or degrees. But I'm just going to leave it in revolutions for now. What else do I know? Somebody said it, what? Right, I know theta initial, you said? Yeah, so theta initial equals 0. What else?
W naught.
Right, omega naught is equal to 0. Right, that's because it says that it's at rest, and so it's equal to 0. And I want to know what is omega. And so if I look over here, which of these quantities do I know or not know? I don't know omega. Anything else? Right, so how do I find alpha? Right, so I can just take the top one. Theta equals omega naught t. That's 1/2 alpha t squared. Omega naught is 0. So it becomes pretty easy. You don't have to use quadratic. That's 3 revolutions. 1/2 alpha times 2 seconds squared. What is it giving me for my alpha? I have it for me. Okay, well, you don't need the calculator, do you? So, 1.5. Brittany, that's what you got? Or Brittany? Can I call you Brittany? Whatever. All right, 1.5 is alpha, and then it's just a matter of plugging in over here. So I have omega equals 0 plus 1.5 revolutions per second squared times my time, which is 2. So that's 3 revolutions per second. All right. In these problems, it's really just a matter of looking at the problem and asking yourself, what is it that I know and what is it that I don't know, and then finding the right equation and plugging it in. So once you master that skill of sort of reading the problem appropriately, then they become fairly simple. Is this fairly straightforward for y'all? Yeah. Now on the next test, the problems will be paired with stuff that we do in Chapter 8, but you will see some kinematics questions like this that will be paired with other things that we'll get into next chapter. Everybody got this okay? We're able to work this? All right. There's one more topic in this chapter on centripetal acceleration. Can I come away from here? Yeah, oh, wait a second.
I'm tired.
Yeah, I am.
Everything's scary.
All right.
Oh my god, what is this thing around me? Oh my god, it's oxygen. Run away.
I'm going to take this away. All right. All right, so we're going to look now at centripetal acceleration. If you're in the lab, we talked a little bit about centripetal acceleration in the previous lab. Anytime that I have an object that's spinning around in a circle, if I have an object like just a ball on a string, it's a what?
Hit someone.
Yeah. Even if it's traveling at a constant velocity, it still has an acceleration. Why does it have an acceleration?
Because it's always changing direction.
What's that?
That going to the center.
Okay, there is an acceleration towards the center of the path, but it's because the direction is always changing. So even if it's traveling at a constant velocity, at a constant speed rather, its velocity is still changing at a constant rate, not because the magnitude of the velocity is changing, but because the direction is changing. And that type of acceleration we call the centripetal acceleration. And so even with constant speed, the direction is always changing. It's constantly changing. So the acceleration is not zero. And we call this the centripetal acceleration. Different people write it differently. Let's see what I do here. Yeah, I call it AC, where C is centripetal, but you might also see it called AR. And it's called AR because the R means for radial. But I'll use AC, where C just stands for centripetal. You can see it listed in both ways. That centripetal acceleration, as Mark said, is always towards the center of the circle. So if you think about this, if I let this object go, it has a certain amount of inertia, and as it travels around this circular path, it's always trying to move in this direction, right? And so I have to have an acceleration vector that pulls it up in this direction, which instead of causing it to go straight out, is going to make it move in this circular path. So that centripetal acceleration is always pulling it towards the center of the circle. And so if I take it away, what's the direction that the ball is going to travel? Like if I take it away when the ball is, sorry, when I take it away when the ball is at the bottom, what's the direction that the ball will travel? Will it travel straight out, or will it travel sort of up towards the ceiling?
Straight on. If it's straight up, all it up.
Yeah, it's going to travel straight out. So if I take away that acceleration, that centripetal acceleration, then the ball will move straight in the path that it was going initially. So let me see if I can do this. Yeah, there we go. So you'll see, if you let it go right at the bottom, it just continues moving in the straight path at which it was going. All right. Now, this centripetal acceleration is provided by a force. So here, for example, I have my velocity vector, which is tangent to the circle. My acceleration vector, AC, is always towards the center. You write that in words. The centripetal acceleration is always towards the center of the circle. In fact, that's what centripetal means. Centripetal literally means, you might know what it means?
Center seeking.
Center seeking. Yeah, center seeking. So it is an acceleration that's always towards the center of the circle, towards the center of the circular path. This centripetal acceleration is provided, in this case, of a ball on a string, by the tension in the string. So in this case, the centripetal acceleration is caused by the tension in the string. And so if I take away that tension in the string, as in this case, if I just let it go, if I take it away, then it's not going to move in a circular path. So I want you to be clear that the centripetal force is not some separate force, like it's not some separate physical force, that it's always provided by something. So what are some examples of objects that move in circular paths? Can you think of something just sort of in real life, something that moves in a circular path?
Train.
What is it?
Train.
Okay, a train. So a train moves on a track in a circular path. What causes it to accelerate in that way? What causes the centripetal acceleration? What's the force that causes it? The track, right. So the force, the track actually pushes on the train and moves it into a circular path. What about when you're out racing or whatever in your car and you go around a curve? What causes the centripetal acceleration in that case?
Embankment.
Okay, yeah, if you have an embankment, actually part of the normal force acts as your centripetal, causes your centripetal acceleration. What if you're just on a flat surface? What is that? Right, the static friction. So when you have those wheels rolling, remember you have static friction, and that static friction is what causes your centripetal acceleration. Those classes of forces are called centripetal forces, and we can calculate them just from Newton's second law. Let's see, was there something out about it? Oh, one more thing, actually. We can also, so we have our centripetal acceleration, AC. We can find it, it's just V squared over R. And so this is our expression to calculate our centripetal acceleration. So for example, if I have a string and it's moving here with a, let's see, a radius equal to 1 meter, and it's moving at 2 pi radians per second. And if I want to find the centripetal acceleration, AC, I first need to find V. So V is equal to omega R. R is 1 meter, omega is 2 pi, so V is 2 pi meters per second. Okay, so that's my velocity. And then if I want to find the centripetal acceleration, it's going to be that linear velocity, which is 2 pi meters per second, over R squared, where R is 1 meter. So that's just going to be 2 pi. Isn't R 1 meter?
You have on the AC V squared over R.
Oh, I'm sorry. Yeah, you're right.
What is V squared?
Alright, so v squared over r, so this is squared, so it's going to be 4 pi squared. Meters per second squared. Alright, so we can calculate our centripetal acceleration, and we'll see this sort of come up in some problems, more so in the next chapter, but we'll work through some today. We can also find an alternate form for this, because we know that v is equal to omega r, so we can just do that by substitution. The centripetal acceleration is omega r squared over r, and so then you get the centripetal acceleration as omega squared r. And so you can see that here, our omega was 2 pi. So for example, it's going to be 2 pi radians per second squared times the radius, which is 1 meter, which also gives us 4 pi squared. Right, so those are just a couple of different ways that we can calculate our centripetal acceleration. Again, centripetal acceleration is equal to v squared over r, or you can also say that it's omega squared r. There's going to be a lot more equations in these next few chapters. So on the next test, I'm going to give you guys an equation sheet. I'll make that available to you soon. I'll put it on the website. And that way you don't have to worry about memorizing all the equations and what have you. But don't be lulled into thinking that it helps a lot, because I found that students that sort of rely upon that equation sheet a lot don't do as well, because there aren't that many equations, honestly, but you really need to sort of know them so you can do them quickly. All right? But I'll make that available to you soon. All right. So as I said, the centripetal force is a term used to describe an already existing force. So like, for example, with the hand and the ball, the string with the ball going around, the centripetal force is caused by the what? Right, the string, or what type of force? What, Brittany? Yeah, the tension. So it causes by the tension. Is this force that causes the ball to change the direction. So the tension is the centripetal force. So if we have a centripetal acceleration, we have to have a force that causes it, and we can calculate that force . It's just going to be Fc is equal to the mass times the centripetal acceleration, and that's just going to be mv squared over r. So this is our centripetal force, our expression for the centripetal force, and we'll use it in a couple of different problems. I'll do an example now to show you. I like to do this thing whenever we get mustard bottles, like we like brown mustard on sandwiches, and whenever the mustard bottles get really empty, it's hard to get the mustard out. They're squeeze bottles. So what do you do to get the mustard out? Yeah, I mean, you can shake it like this, and that sort of works, but that mustard's pretty thick. It's hard to get it all out. So my kids really like this. I'll take the mustard bottle and hold it in my hand, and I'll do like a Gonzo thing. You ever seen Gonzo with the head bowling on the Muppets? Yeah, so I take the thing, and I do like this. And it causes all the mustard to move out into the out to the end of the bottle, right, where you want it. But that actually, if you've ever tried that, like try that when you go home, it exerts quite a bit of force on your shoulder because of that centripetal force. It can be quite large because you have you get to a pretty high velocity v, and your r isn't that long, so it causes for a large centripetal force.
What I used to do is I used to get a cup and I put some water in, and I'd have it where I strapped it up with a bunch of strings, and first I'd hold it with my hand and have the string attached around my hand, and then halfway through I'd let it go and make the R really huge.
Mm-hmm.
And I'd be like swinging, and water never leaving the cup.
Yeah, I'll try to bring a bucket next time. We can show you that. It's kind of cool, actually. Let's work through a problem. Actually, I think I have a clicker question right now. Why don't y'all try this one out? So I have an object moving in a counterclockwise circular path as shown at the point shown right here. You cut the string, or you just let the string go. What path will the ball follow? A, B, C, D, A, B, C, or D? Click in. Oh, you got your clicker out. Do you have yours, Scott?
I had my clicker, I just dropped my pencil, and I don't know where it disappeared.
All right, I'll stop at 35. Okay, very good. B is the right answer. And I think there's one more. This is a little more complicated. I have a truck that can go around a flat curve with a radius of 120 meters. There's a maximum speed. With what maximum speed can it go around a curve having a radius of 75 meters? So let me just give you a little hint here. I'm going to start this. But I have this curve, and I have a truck going around it. You want to list the forces that are acting on it. The force that's causing it to go in a circular path is the force due to static friction. So remember, static friction, our maximum static friction is equal to mu s times my normal force. So there are a couple steps that you have to do. You first have to find out what is my mu s, and then you can come back and find out what is your maximum speed around which you can go this curve, around this curve. Your static frictional force is your centripetal force, so you can find that. And then you can find mu, and then you can find the speed going around this smaller curve, which should be a larger or smaller speed, do you think? If you make your curve tighter, what's the speed limit going to do? Go up or down? It's going to go down, right? About 20 more seconds, so if you're still working, you wrap up your answer. Stop at 3:35, 10 more seconds. Okay, let's see. I'm not sure what the right answer is. I'm going to go ahead and mark C. But you know it has to be either A or C, right? Because you're making this curve tighter, and so the speed limit will have to go down, the minimum speed, or the maximum speed with which you can go around it. So let's see. The first thing you want to do is find out what is the static frictional force required for it to go around. And the static frictional force is equal to my centripetal force. It provides the centripetal force that causes this truck to go around this curve, and that's equal to mv squared over r. Let's see, I know a few things, but I don't know the mass of the truck. Is that a problem? No, it's not a problem, because your static frictional force is equal to mu force normal, and so that's also equal to mu s times the weight, which is mu s mg. So this is my static frictional force, or at least my maximum static frictional force, which is, since I'm looking for limits here, that's all I need. So I can say that mu s mg is equal to mv squared over r. Remember, all I'm saying here is that my static frictional force is the same as my centripetal force. It provides that centripetal force, and if you notice, my masses cancel. What implications does that mean? Like for a road, a vehicle going around a curve, for setting your speed limit?
It's not dependent on mass.
Right, so it doesn't matter if you have like a little Honda Civic or if you have a great big Ford F-350 or whatever, that the same speed limit is going to apply. There is a little bit of a caveat in that, like for really big trucks, their center of mass is different, and so they're more prone to tip over because their center of mass is a lot
A
higher.
fire truck with 2,000 gallons of water in the back.
Right.
With a
Yeah.
500-gallon tank of water in the back.
Mm-hmm. But as you have a larger vehicle, it increases the normal force, which increases the frictional force, which provides for a larger centripetal force. All right, so here I can figure out what mu is. So mu s is equal to v squared over gr. And so I can find mu. That's going to be 25 squared over g 9.8 times r, which was 120 meters. You might know what that is. 0.53. All right, so that is my coefficient of friction, and that doesn't change, like unless my road conditions change. Like if the road becomes wet or icy, then obviously it's going to be different. All right, so now I have a new curve, and I want to figure out what is the new speed, the maximum speed. So I just start back where I was. Fs equals mv squared over r, and that's going to be mu mg. That's my static frictional force, equals mv squared over r. Cancel my m's, and I solve for v. So v is going to be the square root of mu gr. And now you know mu, so you can apply it to different radii curves. It's going to be 0.53, 9.8, times r, which is 75 meters. Is it, what is it?
19 point something, so it's 20.
Is it seriously?
Yeah.
But didn't y'all put C? Okay, yeah, it should be 20. Sorry. I was just going with, I didn't know what the number was, so that's equal to 20. I'm not sure what y'all did to get 15. Do y'all know what you did wrong to find 15? Or are you just guessing?
You estimate.
You estimate. Okay.
I did a proportion, I got 15.
A proportion.
I thought that's-
Oh, like 120 to 25 is equal to something to 75?
Basically.
Something like that? Okay. Yeah, it's not that simple. You can't do it that way. All right. Let's work through a different problem, combining some of the stuff that we've done already, like with inclined planes and what have you, to find the maximum speed. Let's say that instead of having, this is a flat bank curve, or a flat curve, let's say that we have a bank curve, which is another way that you can change the speed, right? When you have these exits coming off of highways where you have very sharp turns, they always bank, or they usually bank the road, and that causes you to get, that allows you to have a higher speed without actually sliding off the road. So let's consider that. Let's say that we have a, I don't know, a 10-degree curve here, 10-degree bank. I know that doesn't look like 10 degrees, but let's say that it is. And I have a vehicle here. Let's say that the coefficient of static friction between the tires and the road is 0.5. And I want to know what is the maximum speed. All right, you want to start just by drawing all of your forces here. So I just have a few forces. I have 3 forces. What are they? Okay, I have the normal force. It points perpendicular to the surface. What else do I have? All right, one of my forces some of my forces are gonna act as centripetal forces, but I'm not gonna label it separately because it's gonna be some other physical force. So the centripetal force is provided by other forces. What are the other 2 physical forces that I have? Okay, I have the weight, Fw. What else? Okay, I have the static friction, Fs. All right. Let's see, what would be these? I'm going to draw my coordinate system here a little bit differently than I've done before. You could do it the way we've done it before, but I'm just going to draw it a little bit differently. I'll show you why in just a second. I'll draw it here. So this will be my x-axis, and this will be my y-axis. Now if this angle is 10 degrees, I'll let you do this on your own, but if that angle is 10, then this angle is also 10. And actually, I have a mistake here. What's my mistake in my vector diagram? You'll see one in one of the forces. Fs should be the opposite way, because this car is going to tend to move up the inclined plane, and so the static frictional force will actually be opposite that. So my Fs will be in the opposite direction here, Fs. And if that angle is 10 degrees, then that means that this angle is what? 80 degrees. All right, so if I redraw this, sort of clean it up a little bit. Here's my axes. I have a normal force that comes off of here at 10 degrees. And then I have my static frictional force is here at 80 degrees. And then I have my weight. All right. In this case, what's going to cause my centripetal force? What are the forces that cause this car to move around in the circular path? There are 2 forces. What are they? Right, the normal force and the static friction. But look, they're just components of those. So I'm going to redraw this, but drawing the components of the forces. So I have Fw, then I have Fs sine of 80. I have Fs cosine of 80. Fn cosine of 10, and then I have Fn sine of 10. All right. So in this case, my centripetal force is given by the sum of the forces in the x direction. So the sum of the forces in the x direction is going to be Fs cosine of 80 plus Fn cosine of 10, and that's going to equal my centripetal force, which equals mv squared over r. I can draw my sum of the forces in the y direction as well. And that's going to be Fn sine of 10 minus Fw minus Fs sine 80. What is the acceleration in the y direction?
0.
It's equal to 0. And this goes back to something I did at the beginning. And what was that I did at the beginning? It was a little bit different. I changed my x and y axes, because if you rotate your axes in this way, your centripetal acceleration is going to have components on both the x and the y axes. But the reason I drew it in this way is so that my centripetal acceleration, which is towards the center of the circle, will be entirely on the x-axis. You could do it the other way, but it makes it a little bit more difficult to do it the other way. All right? So let's look at this. I want to get back to what is v, and I have v over here. What are some things that I'll need to know, or what's an approach that I could take to this to find it?
The mass of the vehicle.
The what?
The mass.
Do I need the mass of the vehicle? Yeah, I think it's pretty sure, yeah. See, does it cancel out? No, I'll need to know the mass of the vehicle. So we'll give you the mass. It's 1,000 kilograms. All right, and then I have two equations here I can solve. I know that Fs is equal to mu force normal. So that's one thing that I can substitute in here, and just gives me then two unknowns in the top equation. And then I have two unknowns in the bottom equation. Oh no, I just have one unknown in the bottom equation. So I can take this bottom one. I have Fn sine of 10 minus mg minus mu force normal sine of 80 equals 0. Can you take that and solve it for Fn? I'm going to let g equal 10 meters per second squared. And you just have one unknown, so you can solve for Fn. Somebody let me know when you get a number for Fn, please. answer for that? I get a negative number. Do I get a negative number?
Yeah.
I'm not sure why that is. Let me look at it. Fn sine.
Cosine 10.
Should it be cosine 10? Where?
For the force to the y x.
Up here? Mm,
Yeah.
unless I drew my angles wrong up here. I'll have to look at this in just a bit. I'll look at it. We'll come back to it. But let's just say that our normal force is 10,000. 31,000 newtons. I'm gonna have to look at it. That number might be incorrect. I'll come back to it and we'll look at it. But once you get your normal force, then you come up from the second equation, whatever your normal force is, and you say Fs cosine 80 plus Fn cosine 10 equals mv squared over r. And here in this case you only have one unknown, and that's the velocity, because now you know Fs, that's mu times the normal force, cosine 80 plus Fn cosine 10. You know the mass, 1,000 kilograms, v squared, and then r I gave you as well. What was r? Oh, I didn't give you r. Well, let's say you're looking for a certain radius. Let's say that r equals 50 meters. All right, and then you can solve for v in that case, once you know Fn. I'll look at that angle. I'm not sure why it came out negative. I'll have to see. I might have had the angle incorrectly drawn. All right. You could potentially see something like that on the next test. I'll let you know as we get closer, because we're going to be doing some other stuff as well. But something that combines an inclined plane with stuff like we've done before. It's a little bit different than what we've done before, just because of the way you have to draw your coordinate systems. But it's largely the same. We're just adding in the centripetal force. All right. Is that exciting for y'all? Like, you look really excited about it. 17 meters per second? Okay. Yeah, I'm going to have to look at the angles, because that normal force should have come out positive. I'm not sure why it did. All right, I think we're out of time now, so we'll pick up next time and do the concept test for this chapter, and then we'll move on into chapter 8. And chapter 8 is a lot to sort of an continuation of this chapter. All right, y'all have a great day. Yeah.
I know what you were wrong.
What was wrong?
Mm-hmm.
The angle drawn incorrectly? Yeah, I thought that was the case. Yeah, so that should have been 80.
Yeah.
Yeah. All right.
So,
So we would
here,
just switch
all
the angles.
wrong. Just switch the
Well, not all wrong. It just switches these angles, right? This becomes 10 and this becomes 80.
Yeah.
Yeah. And this becomes 10 and that becomes 80. Okay. And then it comes out positive. Okay, I'll fix
So,
it. So this would be 80, and that should be 10.
so here is also
All the angles should
yeah.
be switched. I'll look at it next time. Thanks.
I need to talk to you about my class being dropped from Banner. I emailed you about it.
Right, yeah, did you do the ad drop form? I emailed you back. I called the registrar. Did I not email you back?
I did. I didn't. I just have to go to the registrar.
Yeah, we'll go to my office, we'll get the form.
Alright, sir.
I'm sorry, something happened. They didn't know what happened, you know. It might have just been a bug in the system, but it shouldn't incur any fees or anything. If it does, let me know. I'll raise some call there. But sorry for the inconvenience.
It's fine.